This is Algebra 1, Lesson 7.5. We're looking at special types of linear systems. All this means, we know what linear systems are. That's two lines that are going to intersect at one point. So when you're talking about a system, we know we can solve it. The first way we learned was to graph both lines, estimate what that point is, and then see if it works algebraically. The second method we learned was the substitution method, where we plugged them both in, or we plugged in an expression for one variable from one of the equations into the other one to solve for that variable. Then we plugged it back into the opposite equation to get the other variable. So you got x and y that way. Then we learned the elimination or combination method, and that was by putting both of them together when you had an opposite set of coefficients to get rid of one or eliminate one. Um, what we're talking about today is special types. And what special types are, they don't necessarily have one point, or I should say, they don't have one point because they're considered special systems. In this case, when you have two equations that have different slopes, like this red one and this blue one, there's going to be one point where they'll intersect. But we all know what parallel lines look like. Parallel lines are lines that are going to look like this. They'll never cross each other. The ones I just drew probably will eventually. But parallel lines will never cross each other. So if we used the graph and check method, when we graph both of these, they would never intersect each other. So there's no solution to this. So parallel lines have no solution. That's one type of special situation. The other type of special situation, or the other type of special system, is when you have the same line. It may just look different, or it may be in a different form, the same line graphed on top of the other one. So it'll look something like that. In that case, they'll have infinitely many solutions that are the same. So graphing wise, it's easy to distinguish between special situations. Algebraically, it's also easy. That's what I'm going to show you today, though. Algebraically, how to do it. Here's example number one. A linear system with no solution. Okay, so no solution means that they're going to be parallel lines. Remember, that's the symbol for parallel. No solution. You have two equations. Negative x plus y is equal to negative 3, and negative x plus y is equal to 2. The first thing we want to do is we want to get both of these equations in slope-intercept form to where we can see what the slope is and we can see the y-intercept. So we know, looking at this first equation, negative x plus y equals negative 3, just like the bell work, what do we need to bring over from the left side to the right side? Negative x. So you know if it goes from the left side to the right side, you know it's going to become positive. So when you do that, you get y equals x minus 3. For the other equation, negative x plus y is equal to 2. Again, what are we going to bring over from the left to the right? Negative x. When it's negative on the left, when it goes to the right, it becomes positive again. So that equation is going to say y equals x plus 2. The second thing you want to do is graph both of those equations. Both of them are very simple equations to graph. The first one, y equals x minus 3. You know to begin on your b value, negative 3. So remember, your b value is your y-intercept, your y-axis at negative 1, 2, 3. That's where you begin right there. Now, your slope is harder to see, but y'all are big enough in here at this point, you should know what the slope is. It's 1. And remember, all slopes are written as fractions, so it's 1 over 1. So from that point, negative 3, we go up 1 and to the right 1, and we have ourselves a point like that. So if we drew a straight line through those two, it would look like this. Not like that. Hopefully straighter than that. It would look like that. The second equation begins at 2. So on your y-axis again at 1, 2 is where you begin. Your slope is the same 1, which is also over 1. That tells you to go up 1 and to the right 1. We all know how to fool with slope. Positive tells you to go up. Positive tells you to go to the right. So up 1 and to the right 1. There's our second point. 2 points tell us to draw a straight line through the 2 points, and it'll look like this. So those are parallel lines. was able to draw them a little straighter on your sheet than I drew them on the screen. That's good. But those are parallel lines. At what point is going to be true for the red one and the blue one? Where will they cross each other where we can plug that point in and get two statements that are the same? Never. So there'll be no point right there. So because the lines have the same slope, now this is the other part, but different y-intercepts. One of our y-intercepts is -3, that's the red one. The other one is +2, that's the blue one. Same slope, different y-intercepts. They'll never cross each other, so there is no solution. That's method number one. Some of y'all were asking about two methods. That's method number one. Method number two deals algebraically how to do it. This is the way that most of us would rather do it, where we don't have to fool with the graphing, especially where we don't make a mistake drawing it. So substitution is the second method we learned how to do with systems. It says equation 2 can be rewritten as y is equal to x plus 2. We did that already. In place of y, you could sub in that value or that expression x plus 2. So here's equation number 1. Negative x plus y is equal to -3. In place of y, so right here, we're subbing in x plus 2. So that's all that happened for the second line. In place of y, x plus 2. Again, this is a recap of substitution from 2 weeks ago. You can combine these now. Negative x plus x, when we put those two together, gives us no more x's. They cancel out. So what you're left with is something right here. 2 is equal to -3. Notice, though, that all of the variables are gone. They went away. They eliminated it. Anytime you eliminate all of the variables, so algebraically, right now, tell this to yourself until you got it. Anytime you eliminate the variables, it's either going to be every solution or no solution. Okay. If it is a false statement, that's easy, no solution. False statement, just like this, 2 is equal to -3, is eliminated. There's no solution. So you can do what point do they cross? What point makes the system true? There's no solution. Remember, this is shorthand for no solution, null set. So you got two methods. One of them is to graph them and to see the parallel lines. The other one is to sub it in or plug it in and see that you get either a true statement or a false statement. So on the back, show me how this system has no solution. So you can do it, again, one of the two methods. If you get stuck, turn back and take a look at it. Either graph them and show. We know they're going to be parallel lines. Either show it or do it algebraically. Plug it in. Okay, let's take a look at it. Negative 6x plus 2y is equal to negative 8. Two different methods again. Go through both of them real quick. That's how quick they are to do. Take the first equation and make it into something you can graph. If you graph it using the intercepts, that's fine. You don't even have to change the equation. But according to just to follow the methods we did a second ago, move over negative 6x. When you do that, you got 2y equals positive 6x minus 8. Then divide by 2. Divide this, this, and this, everything by 2. So y equals 3x minus 4. So the first equation, 3x minus 4, we begin at negative 4 right there. Remember your slope, 3, is always a fraction. So if it doesn't show 1, make it 1 by putting it over 1. 3 divided by 1, or 3 over 1. That tells you to go up 3 and to the right 1. Up 1, 2, 3, and to the right 1. So there's 2 points. We can draw a straight line right through those 2 points with no problem. Looks something like this. The other equation is easier to convert to slope-intercept form because there's only one step. The only thing you got to move over is negative 3x to the other side. If it's negative on the left, it becomes positive on the right. So when you move it over, it says y equals positive 3x, positive or plus 7. So again, mx plus b. Your b value tells you to begin right here at 7, right here. Your slope value, again, is 3 over 1. That tells you to go up 3 and to the right 1. So up 1, 2, 3, and to the right 1. This is showing, and I wish I could draw straighter lines up here a little bit better. Let me do it this way. This is showing two parallel lines. The only reason they're not perfectly straight on my screen is because the blue one, I didn't use the straight line. But that's showing two parallel lines. And what that's also showing is that there's never going to be a point where they're going to intersect. So the other method was, without having to fool with the graphs at all, is to just do it algebraically. So we'll go back to this step right here. Y equals 3x plus 7. And this step right here, y equals 3x minus 4. So we have two equations. Both of these are in slope-intercept form, or both of those are isolated. So what you want to do substitution-wise is take this expression 3x minus 4 and sub it in, since it says that's what y equals. So instead of y, 3x minus 4 can go right there, is equal to the rest of it, 3x plus 7. So you want to collect your variables on one side. Subtract 3x right here to bring this one over to this side. Minus 3x minus 3x. 3x minus 3x we know is going to be 0. It's going to eliminate. So what you have is negative 4 is equal to positive 7. So you have a statement right here that you need to check. The variables are eliminated. You have a statement, negative 4 is equal to 7. That is not true. Therefore, there is no solution to this. So that's how you show, using both methods, that there's no solution. The second example is if there are many solutions. Anytime the variables are eliminated, it's either going to be no solution or it's going to be an infinite amount of solutions. Watch what this means. So the first method is to make both of them into slope-intercept form. So for the first equation, this one, red one right here, bring 3x from the left to the right. You know positive 3x, when it moves over, it becomes what? Negative 3x. So y is equal to negative 3x minus 1. The other equation, you got to do it in 2 steps. It says negative 6x minus 2y is equal to 2. So we need to bring over or move over negative 6x first. You're left with negative 2y on the left equals positive 6x, positive 2. Not quite y equals mx plus b. One more step. You got to divide by negative 2 to get y by itself. Divide this and this by negative 2. All of those are positives divided by negatives, so you know they're going to come out to be negative. So y equals negative 3x, negative 1. That's slope-intercept form right there. Y equals negative 3x minus 1. Before you do anything else, compare your red and your blue equations, or the two equations. Notice they are exactly the same. Y equals negative 3x minus 1. If you graph both of those, again, your b value for the red one would tell you to go negative 1. It would tell you negative 3x, or negative 3 over 1, tells you to go down 1, 2, 3, and to the right 1. And it would go through at these points right here. Your line will look just like that. The other equation Your other one, the blue one as I have it up here, um, is the same. You begin at -1. You go down 3 and to the right 1. Notice everything is exactly the same. We're sharing all of these points. That's not a coincidence. We're sharing all of these points. And you get the same line going right through it. So it looks just like that. So the blue and the red in this case, or both equations, share every single point. So there's an infinite amount of points that make it correct. There's an infinite amount. So from these equations, you can see that that it represents the same equation. So every point on a line is a solution. Again, before you do any graphing right here, you can do that. Method number two, method number two is simply showing algebraically how to do it. This one's saying linear combination. So you have two equations, 3x plus y equals -1 and -6 minus 2y equals 2. They're stacked correctly. X is on top of x's, y is on top of y's, constants on top of constants. So what you want to do is you want to get one of them to eliminate, one of the variables to eliminate. The easiest one to do is to multiply the first equation by 2 because you want this 3x to become positive 6x because you have -6x right below it. Remember, you want opposite coefficients. So 6x and -6x will eliminate. So 3x times 2, remember, you need to multiply the entire thing. So that times 3x is 6x. That times y is positive 2y. And that times -1 is -2. So you have two equations now that have opposite coefficients. When you put 6x and -6x together, they eliminate each other. Notice this is gone. When you put 2y and -2y together, they eliminate each other. That's gone. And when you put -2 and +2 together, they eliminate each other. That's gone. So notice what you got. You got something that says 0 is equal to 0. You have a true statement. It doesn't have to say 0 is equal to 0. It just has to say a true statement. It might say 3 is equal to 3 or 4 is equal to 4. Any number is equal to the other. But a true statement means it's the exact same equation. Means it's the exact same equation. So again, one more time on the back. Show that these equations or this system is the exact same equation. Show that it has infinitely many solutions. So we can show this two different ways. Again, two different methods. The first one is to graph both of them. See, it's the same equation. So take this equation and move it in a slope-intercept form. Negative x has to move over, just like the bell work. 2y equals negative becomes positive on the right, -2. Not quite slope-intercept form. You got to divide by 2 on both sides. Divide this. Divide everything on the right by 2. Remember, this is 1x divided by 2. So y equals 1 over 2x. And then again, a negative divided by a positive is going to be a -1. So that's y equals mx plus b. The other one will do the same thing. We wanted to say slope-intercept form, y equals mx plus b. Move 3x over, and it becomes negative 6y. Don't lose the negative there. Equals 3x becomes negative 3x on the right, and it's positive 6. Again, not quite y equals mx plus b. You need to divide by negative 6. Divide everything on the right by negative 6. Y equals a negative divided by negative is a positive. The number 3 goes into both of these. It goes into 3 once, and it goes into 6 twice. So 1 half x. And then a positive divided by negative is a negative. 6 divided by 6 is 1. So just at this step right here, before you graph anything, you can see that the equations are exactly the same. Y equals 1 half x minus 1. So when we graph both of those, they're going to stack on top of each other. Y equals 1 half x minus 1. Negative 1 is where you begin. So right there. Tells you right here your slope is 1 over 2. Tells you to go up 1 to the right 2. So up 1 and over 2, your point's going to go right there. And when you draw a line through those 2 points, it'll look like that. The other equation, again, your b value is negative 1. You start right there, or you begin right there. Your slope is the same, 1 over 2. Go up 1 to the right 2. Same point, same line. That's why they share infinitely many solutions. That's one way to do it. The other way to do it is to use the elimination or combination method. Take these two equations, negative x plus 2y equals negative 2, and 3x minus 6y equals 6, and change one of them or both of them to where you have opposite coefficients. If you multiply the top equation by the number 3, if you multiply the top one by the number 3, 3 times negative x gives you negative 3x. That'll make it where we can eliminate our x's. 3 times 2y is positive 6y, and 3 times negative 2 is negative 6. Look how these two equations look. 3x minus 3x, that's eliminated. Negative 6y minus 6y, that's eliminated. And 6 minus 6, that's eliminated. So you're left with something that says 0 is 0. This is the part where you check the truth value. If it's true, that means they're going to share infinitely many solutions. So the solution to this system is all real solutions right here. All real solutions.